Hi, welcome to part 1 of the SAR ADC. This here is the clock circuit of the device, which operates around 10 kHz, and that's confirmed by both this oscilloscope photo here and this TMM photo. As we can see, a square wave is indeed generated by the circuit with a period of just under 104 microseconds and a frequency of around 10 kHz. The clock signal generator is relatively simple, so here's how it fits in with the rest of the circuit, as well as an overview of the circuit as a whole. Starting when the switch is flipped, this sample and hold IC here temporarily holds the voltage input on the analog input that will be read. This prevents the voltage from changing during the conversion process, which could lead to a distorted digital signal. Once the voltage is stored in this capacitor on the sample and hold IC, the conversion process starts. The first thing to understand is that this bank of D flip-flops here stores the results of each successive approximation. Each flip-flop is clocked by a successive shift register pin from IC number 1. So this means that on the first clock cycle, this clock goes high, on the second, this clock goes high, on the third, this one goes high, and so on, meaning each one is updated individually on a different iteration. Each flip-flop is also preloaded with a value of 1. So on each iteration starting from the top, the voltage is tested by assuming that the bit is high. Then, if it is high, the comparator will echo that 1 back onto the data input of that flip-flop, and as the clock is pulse high, it will remain a 1. If that assumption was incorrect and it was actually a 0, then when it goes through the comparator, the analog voltage is being compared against will cause the output of the comparator to go low, which is again tied back to the data input, and so when the clock is pulse high, Q, or the output, will now change to a 0. This process is then repeated for each bit until all 7 bits are solved and presented on the parallel output interface. So for example, if the voltage being tested were 4.21 volts, which is 11101011 in binary, or that's the value the ADC would spit out, here's how the process would work. So I've gone ahead and put in all the initial values. So as we can see that right now, on the first clock cycle, a 1 is presented on the MSB of the DAC, whereas 0s are presented on the rest. So the DAC is going to output 2.5 volts because it's half of 5 volts. So right now, 2.5 volts is being compared against 4.21 volts. And so 4.21 volts is greater than 2.5 volts, which means the comparator is going to output a 1. So this 1 is going to stay. So this remains a 1. Next, Q0 of the shift register goes high, which presents a 1 on this AND gate, changing this output to a 1. So the DAC now is outputting 1, 1 with 5 zeros, which corresponds to the voltage 3.78 volts. Again, 4.21 volts is still greater than 3.78 volts, so the comparator keeps the 1 on this output. So we can fill in the status register right now. So D6 and D5 are 1s. Next, this process repeats on the next pin, which again bumps this to a 1, bumping this to a 1. And so now it's going to compare it to the value 1, 1, 1, and then 4 zeros. So this voltage that's outputted is 4.41 volts. So now we have 4.41 volts on as the reference voltage and 4.21 volts as the voltage being tested. So 4.21 volts is now less than 4.41 volts, which means the comparator is going to output a low, which is going to change the third output to a 0 and store a 0 in this D flip-flop. And so we can put a 0 on D4. And then, as we can see, process is going to continue, and eventually what we do end up with is 1, 1, 0, 1, 0, 1, 1. We can see that we have the beginning of that, 1, 1, 0. So essentially the SAR ADC continuously guesses that the voltage is above a certain threshold, then checks if it's above that threshold using a comparator, and then updates the data bank accordingly and continues on the next iteration. This guarantees that every single measurement using a SAR ADC will take the same number of clock cycles, which allows it to be used in precision and timing sensitive applications. Thank you so much for watching. This is a quick overview of how the SAR ADC works, and I hope you learned something.